In this lesson, we're going to be learning about what a radical is and how we're going to be able to simplify expressions that involve radicals. So let's take a look first at an example of how a radical comes about. So we know that if we square 5, the answer is 25. And that's because 5 multiplied by itself gives me 25. Now also, if we square negative 5, the same thing happens because negative 5 times itself also gives me positive 25. So there should be some sort of process that reverses this process of squaring to determine a number that multiplies to give us 25. And we refer to that as a square root. So the square root of a is simply saying what number multiplies by itself to give me the answer of a. So every time we take a square root, we're really just asking this question. So notice that 5 is a square root of 25, but we should also recognize that technically negative 5 is a square root of 25. But when we see this symbol, this radical symbol, this will always and only represent the positive or principal root. If we wanted to get the negative answer, then we would put the negative symbol in front of the radical. So the negative radical represents the negative square root of a number. So in other words, the square root of 25 is equal to 5, and only 5. We don't say that the square root of 25 is 5 or negative 5. If we wanted to say negative 5, then we would have the negative square root of 25. So let's take a look at this symbol, this expression, and recognize that that symbol is referred to as the radical symbol. The quantity that we're taking the square root of is referred to as the radicand. If you look at the expression as a whole, the expression is referred to as a radical. So notice that there is no real number that multiplies by itself to give a negative number, which simply means that you can't take the square root of a negative number. And the reason for that is that numbers would have to have opposite signs in order to get a negative number, and therefore they wouldn't be the same number. So if you take a look at the square root of 25, the reason that's 5 is simply because 5 times itself gives 25. But if I said the square root of negative 25, nothing could multiply by itself to give me negative 25. So the radicand must be greater than or equal to 0. So since the square root of a number must always be positive, that's something to keep in mind when we start to take square roots involving variables. So notice that the square root of x squared is saying what times itself gives me x squared. So you would expect that it would just be x. But notice that x squared is positive, yet it's possible that the value being squared was originally negative. And so we can't simply say that the square root of x squared is x and just cancel out those quantities. Instead, we have to say that the square root of x squared is the absolute value of x, so that we ensure that the answer is positive. So in other words, we can't necessarily just cancel the square and the square root symbols. So let's take a look at a reason why. If you were able to just cancel the square root and the square, we would say that this answer is negative 6. But the square root symbol implies that the answer is always positive, and therefore what we have to do first is recognize that the square root of negative 6 quantity squared is really the square root of 36, which is 6. So what we could have done is canceled the square and the square root as long as we recognize that it's the absolute value of that quantity. Now it's a little less obvious when you're dealing with square roots of variables. And so now we're trying to think, well, what times itself gives x to the 12th? So we could rewrite this as x to the 6th squared. And if you now cancel the square and the square root, the answer would be the absolute value of x to the 6th. But think about this, if the exponent is even, that would force the output to always be positive anyway. So in this particular situation, it's not necessary to actually write the absolute value bars, so we could just say that the square root of x to the 12th is x to the 6th. So when the output of a radical expression has an odd power, we need to include the absolute value bars. For instance, the square root of x to the 14th. So just like we could reverse the process of raising it to a power of 2, we could also really do this for any power. So if I wanted to take the cubed root of 8, that's simply saying what number multiplies by itself 3 times to get 8. So you could rewrite 8 as 2 to the power of 3, and then recognize that the cubed root of 2 cubed is 2. So that index, or the quantity in front of the radical, or rather in the tail of that radical symbol, tells us how many of the same factor we are actually looking for. So in general, if we wanted to find the nth root of a, which is denoted by this symbol of the nth root of a, and we say that the nth root of a has some answer called b, then all that means is that b to the power of n will equal a. So we can see this a little more accurately when we look at this example. So if I say the 4th root of 81, I don't know the answer, so maybe I just say that the answer is b. Well, if the 4th root of 81 is b, then what we just said in red up above is that implies that b to the power of 4 is 81. So if you think through that for a minute, that would mean that the 4th root of 81 is 3. Because that implies that 3 to the power of 4 is in fact 81. So the 4th root of 81 is saying what times itself 4 times will give me 81. So if x happens to be a real number and the index is greater than 1, then that must mean that that index is telling us how many of the same factor we would need to see. And therefore, if that is an odd integer, there can only be one answer. But if n happens to be an even integer, like a square root or a 4th root or whatever it might be, then our answer is the absolute value of x. And therefore there are 2 answers, one which is positive and one which is negative. So if I wanted to simplify the 5th root of negative 32x to the 15th, remember that that's saying what multiplies by itself 5 times to get us negative 32x to the 15th. So we could really break this up into 2 parts. We could say the 5th root of negative 32, or rather negative 2 to the 5th, times the 5th root of x to the 15th, or rather the 5th root of x cubed to the 5th. So what I tried to do here is force each quantity to have a 5th power, and therefore when I cancel out the radicals, that gives me negative 2x to the 3rd. Now I don't need absolute values because this is an odd index. When we can take odd roots of negative numbers, since a negative times itself an odd number of times becomes negative. Just think about the cubed root of negative 1. The answer is negative 1 because that's what multiplies 3 times to get negative 1. We just can't take even roots of negative numbers. So if I take a look at the 4th root of negative 16, the 4th root of negative 16 is saying what multiplies by itself 4 times to get negative 16. But you should see that that's impossible, because notice that if I multiply something 4 times by itself, then the answer will have to be positive. So notice that this is not 2, because the 4th root of 2 to the 4th is 2. And notice that the 4th root of negative 2 to the 4th would give the 4th root of 16, not negative 16. So that's also not true. So that just simply means that this is not a real number. So when taking the even roots, you have to make sure that you're taking the even root of a positive quantity, while if you're taking an odd root, it's possible for that radicand to be negative.